So what I want to do in this lesson is I want to continue talking about these ionization energies. So just as a reminder, so the first ionization energy of an element is the minimum energy in kilojoules required to remove the most loosely bound electron from each isolated atom in a mole of an element in its ground state. So generally there's a simple formula that you can use to represent this first ionization energy. So it's X. So you can write it like this. So it's X in gas form. So X represents whichever particular element you're dealing with. And then you have X plus, because you're turning it into an ion. Then you have, so it's still in a gas. And then you have this free electron. If you take the electron off, you're going to have a free electron. So it'll kind of look something like this. And generally the unit is the kilojoule per mole. Kilojoule per mole. So when you're looking at hydrogen here, for example, its first ionization energy is 1313 kilojoules per mole. So it takes that amount of energy to take off the most loosely bound electron in a mole of hydrogen atoms. And just to remember as well, when you have 1 mole, so 1 mole is equal to 6 multiplied by 10 to the power of 23 atoms. So if you have 6 multiplied by 10 to the power of 23 atoms of hydrogen, it will take 1310 kilojoules of energy to take off its 1 electron that it has. So if we think about hydrogen, for example, so hydrogen is the first element on the periodic table, so it has one positive charge, or 1 proton, and it has 1 electron. So if you had, so this is kind of the electronic configuration of the element. Now if you had, let's say, 6 multiplied by 10 to the power 23 atoms of hydrogen, and you applied this amount of energy to that sample, you will take off this outer electron for all of those 6 multiplied by 10 to the power 23 atoms of hydrogen. So that's kind of the way that it works. Now if we have a look at this then, if we have a look at this table here, so if we have a look at this table here and we kind of look at some of the trends that we have, so what we can see is generally as we move, let's say from left, as we move across the periodic table, as we move across this way, the ionization energy, so this energy, it generally increases. So the ionization energy goes up. So as you move across. Now there are some exceptions to that. Now it makes sense as well, because if you think about it, as you move across, as you move across a period, so as you move from here to here, what's happening is the amount of positive charge within the nucleus is increasing. So as a result of that, the electrons out here, the outermost electrons for the atoms, are going to experience more of a pull from the nucleus of the atoms. So they're going to experience more of a pull from the nucleus of the atoms. So the way to kind of think about it is, as you move from left to right, the positive charge in the nucleus increases. Now also as well, if you like stay on the same period and you move, let's say, from left to right across here, not like the number of electrons that are between, like the number of layers of electrons between the nucleus and the outermost electron stays the same, but the positive charge in the nucleus increases as well. So as a result of that, as we move across here, the pull on the outer electron becomes much stronger, so therefore there's more energy that's going to be needed in order to pull the electron off and to take the electron off the atom because of that strong pull. Now there are some exceptions to that, which I kind of want to just look at and talk about. I want to just talk about that very briefly. So, and also another thing you can like basically think about is, so as you move from left to right, the nuclear charge increases because you get more protons as you move across from left to right. But not only that, the radius of the atoms also decreases. And as a result of that, because the radius decreases, again, that's going to make it harder. There's going to be more of a pull then on the outer electron from the nucleus. So therefore, that's why you have these ionization energies that increase. But if we have a look here, if we have a look at the second period here. So, and if we have a look, so we see lithium is 519. We see that beryllium is 900 and boron is 799. So we see that, and then what happens is you have carbon that jumps up to 1090, nitrogen goes to 1400, and oxygen goes to 1310. Now what I want to look at is these two, first of all, these two atoms here. So beryllium and boron. Now what we would expect is that beryllium would have a higher ionization energy based on its location on the periodic table, but it actually has a slightly lower ionization energy than boron. So what I want to do is I want to kind of look at these two here. So I'm going to map out, so imagine, so this here, so this is boron, and then, sorry, beryllium, and then this is boron here. So what I want to do is I want to look at the electronic configuration for both of these and see if that gives any indication of why boron has a higher or has a lower ionization energy than beryllium. So first of all, if we look at the electronic configuration for beryllium, so the electronic configuration for beryllium, it looks like this. So it is 1s2, and then it's 2s2. So that's its electronic configuration. So what does that mean? So it has 4 positive charges in the nucleus, 4 positive charges, and then its electrons. So this here tells us that we have 2 electrons here. So that's this, that's the 2, and then it tells us then that the other 2 electrons are here. So this is the arrangement, if you like, of beryllium. Now if we put over here, if we look at boron, the electronic configuration for boron, then it's, so it is 1s2, 2s2, and 2px1. So 2px1. Okay, so what we can see here is that it has 2, so it has 5, so it has 5 positive charges, 5 plus, and then its electrons are arranged like this. So 1, 2, 3, 4, and then the 5th one is up here like so. So these, so for beryllium, these 2 here are the outermost electrons, and for boron, this here is the outermost electron. So what we can see is that if we take boron, for example, So we see here boron, this electron here is going to be much easier to take off than one of these electrons here. The reason being is because it's physically further away from the nucleus. It's physically further away, and then also as well, these two electrons here, which are in the lower sub-energy level, they're actually going to exert a force. They're going to push this electron away, and as a result, that's going to make it much easier for this electron. So these two electrons here, they're going to repel this outer electron, and because it's the outer electron is positioned here, which is actually physically further away from the nucleus of the boron atom, it's going to be much easier to pull this electron away, because these two are going to be pushing it away and repelling it, and it's also physically further away as well. So what you get is you get a screening effect from these two electrons, and also as well it's physically further away. Whereas if you look at beryllium, which is here, you can see that the outer atoms or the outer electrons, should I say, are much closer to the nucleus, and they're also within a single orbital as well, which makes them much more stable. So as a result of that, because they're much closer in distance to the nucleus of their atom, it's harder to pull these away. And this is reflected in the difference you see. So for example, beryllium has a first ionization energy of 900 kilojoules per mole, whereas boron has a first ionization energy of 799 kilojoules per mole. So it's just slightly, it's a fair amount less than beryllium, for example. So this, as a result of this element here will have a lower first ionization energy, even though, you know, going by the trend, it should have, if you're to look at it going from left to right, it should have a higher ionization energy, but it doesn't, because of the arrangement, because of these sub energy levels that we have here and the arrangement of the electrons. So that's like these two elements here, or these two atoms, are the exception, are one of the exceptions to the rule along this period. And also as well, you can see that beryllium has a full outer electron shell. So for example, there's this sub energy level is full, whereas, and that makes this more stable, as in harder for you to pull the electron off. Whereas with beryllium, whereas with boron, should I say, the outermost energy level, sub energy level, is not completely full. You only have one electron in here, so that also makes it just a little bit easier to pull it away. Also as well, what we can see is there's another exception to this rule as well. If we look at nitrogen and oxygen, for example, nitrogen has a lower first ionization energy level than oxygen, and you would expect it to be the other way around. So let's just have a look at the electronic configuration for both of these elements as well on the periodic table. So we can just scroll this across. Okay, so let's have a look at these. So we'll do, so let's say this is nitrogen here, and then this is oxygen. So nitrogen, so let's have a look here. So the electronic configuration for nitrogen then is, so it's 1s2, 2s2, so, and then it's 2px1, 2py1, and then 2pz1. So this is the electronic configuration. So what does that look like? So you have 2 electrons here, you have 2 more electrons here, and then you have these the three remaining electrons, 1, 2, 3. So this here, so it's going to have 1, 2, 3, 4, 5, 6, 7. So it has 7 protons or 7 positive charges here. Now if we take oxygen then, on the other hand, so oxygen's electronic configuration, so it looks like this. So it's going to be 1s2, 2s2, 1s2, 2s2, 2px1, 2, that should be 2px2, so that's 2px2, 2py1, so 2py1, and then it's 2pz1. So what does that look like? So you have 2 electrons here, you have 2 here, and then you have 2 in this. So this is the x, this is the y, and then this is the z suborbitals, or sub-energy level, should I say. So it looks something like that. So the electrons are in here singly, like so. So what we can see then is that, so this is the way the electrons are arranged. So oxygen, for example, has a lower ionization energy than nitrogen. So why is that? So really, like what it goes down to, like if you take, so if we have a look here, so nitrogen, like the outermost energy level and the outermost electrons are going to be these guys here, okay, and the outermost electrons for oxygen are going to be these guys here. Now these are all singly filled, so it's just a little bit more stable than this. So what happens with oxygen is, because you have 2 electrons here in this energy level, so this energy level, this orbital here is full, but then these are singly filled. Now what happens is these 2 electrons here, they actually repel each other, and as a result they also repel these 2 electrons here as well. So what that means is that there's more of a push away from the nucleus caused by these, there's more electrons in a smaller space with oxygen than is the case with nitrogen. So here you have 1, 2, 3, 4 electrons in this space, whereas with nitrogen you only have 3 electrons in this space as well. So that extra electron causes it repels the outermost electrons, and as a result of that, it's just a little bit more easier to pull away one of these electrons, because there's more negative charge packly dense, or more densely packed closer to each other, and as a result of that, the ionization energy level for oxygen is lower than the ionization energy level for nitrogen, and that's all got to do with the way the electrons are arranged here. So if you think about all of these electrons here, they're negatively charged, so they're going to be repelling each other, and the same here, these are all negatively charged and they're all going to be repelling each other, but there's more in the same space, there's an extra electron in oxygen, so as a result of that, you're going to get extra repulsion of these outer electrons as a result of that. So you have more negative charge in the one space, so that will mean it will be easier then for this outer electron, easier than with this arrangement, to pull off one of these electrons, and hence that's reflected in the lower ionization energy level for nitrogen and oxygen. So these are just some of the exceptions in relation to the trends in relation to the ionization energy levels. So what we can see, so then just to kind of revise and just to go back on what we've talked about, as you move down a group, so as you move from, let's say you take a group, so this is group 1, as you move down, what you can see is that the ionization energies, or the amount of energy that's needed to pluck off the outer electron, is reducing. The reason it's reducing is because there's a greater screening effect from the electrons. So as you move down these groups, what happens is the outer electron is further away from the nucleus of the atom, so it's not experiencing as much of a pull from the nucleus of the atom, but also then as well as you get more layers of electrons between the nucleus and the outer atom. So you get a higher screening effect as you go down. And what does that do? The more of a screening effect you have, the bigger the radius of the atoms, and the bigger the radius of the atoms, the further away the outer electrons are from the nucleus, and as a result of that, the easier they are to pull away from the atom. As you move from across a period from left to right, generally speaking, what happens is the ionization energy levels increase. The reason they increase as you move from left to right is because the radius of the atoms reduces. So therefore, the screening effect is also reduced in relation to, like, you have the exact same number of energy levels between the outer electron and the nucleus. They're all the same, let's say, along the period from left to right. But what increases is the number of protons that are present within the nucleus. So as a result of that, the pulling force of the nucleus on the outer electron increases. Now there is the exceptions that we've talked about, so you have beryllium and boron, and you have nitrogen and oxygen, which don't follow this trend, and I've talked about why they don't follow this trend, and it's because of the way the electrons are configured in the sub-energy levels within the main energy groups. So that's generally just the trends that we're looking at when we look, let's say, down the groups and along the periods in relation to ionization energy. So hopefully that makes sense. So thank you for listening.